Hello, everybody. Thanks for attending. My name is Lars-Peter Clausen. I work for Analog Devices, where I work, among other things, on I/O device drivers, the I/O framework, as well as the libiio, and this presentation today is going to be about the latter. The agenda is we will start with a short introduction to I/O. So is anybody here who hasn't heard about I/O before, only has like a vague idea what it is? Yeah, so this is for you. But I also want to take everybody else kind of on a journey to understand what the motivation behind libiio is, why we need it. So this will follow from the recap how I/O works. Then the next step is talk about using libiio, talk a bit about the API, and then we will talk about the infrastructure that we have developed around libiio or with libiio, and then finally a bit of future outlook, like where things going. So short introduction to I/O. IIO is short for the Industrial Input-Output Framework, but it's kind of a bit of a misnomer because it's not really just industrial I/O. It's basically any I/O input-output that's non-human interface device, but in the Linux kernel, the human interface device framework is called the input framework. So for I/O, people had to come up with a different name. And it takes care of all kinds of sensor devices. It's ADCs, DAC, light sensors, accelerometers, gyroscope, magnetometers, and so on and so on. And what was also recently added was support for kind of like these lifestyle sensors, which is kind of like counts your steps, how many calories you burned. So all these kinds of different sensors are part or are handled by the I/O framework. And even like for ADCs, the range goes from gigasample ADCs, like 10 gigasamples, down to high precision ADCs that run with a couple of samples per second. So there's a wide range of different types of devices that are covered by this framework. And it was initially developed by Jonathan Cameron. I think he was working on a university project where he had a couple of sensors connected to some device that was running Linux, and he was thinking, well, wouldn't it be great if there was some kind of standard framework to take care of all these sensors? So he came up with the I/O framework, and he's still maintaining the I/O framework today and doing a quite tremendous job at doing it. And initially it was developed outside of the mainline kernel, but then was merged in 2009 for the 2.6.32 kernel release. And initially it was in the staging area, which is kind of the place where all the stuff goes that still needs a little bit of work, isn't quite finished yet, and saw some, well, I would say a couple of overhauls in there, but then finally, 3 years later, in 2012, it was moved out of staging and is now, well, part of the upstream kernel. The ABI is stable, so it's not going to change anymore. And today, with the latest kernel release, we are supporting up to 220 device drivers. We do have 220 device drivers, but many of the device drivers actually support more than one device. So I guess the number of devices supported is easily more than 500. And if you look at how things are structured inside I/O, you at the top always have the device, which is kind of represents a logical unit for data capture, for data input, data output. And typically this represents a physical hardware device, but in some cases where you, for example, multiple chips on the same die, you might actually end up with multiple I/O devices for the same physical hardware piece. And a device can have attributes, and those have two different functions. First function is to describe the capabilities of the device, and the other one is to configure the device. For example, you could think about that the capabilities would be the attributes explain which sample rates are available, and then changing the configuration would be selecting the sample rate of a device, and this is all done through the attributes. There are also channels. Again, more than one channel there can be more than one channel per device. And these channels kind of represent data aggregation or output interfaces. For example, an ADC would have a voltage channel, temperature sensor, temperature channel, and so on. And again, channels, in the same way a device can have attributes, channels can also have attributes. And then the last piece that we have in I/O is their buffers. And the buffers are used for continuous data input-output. So you usually have some kind of clock either embedded in the device itself or external that decides when the conversion is done. Sometimes this is emulated by using a software timer. But in general, thinking about the buffers, you will get evenly spaced data in your buffer. And again, the buffer can also have attributes, a couple of standard attributes, and drivers can also specify custom attributes if necessary for the buffers. So in the kernel, this looks a bit like this. So we have the structure, the I/O channel spec, and you can see here the example is we have a voltage channel, and these info masks define which standard attributes are available. In this case, we have a separate attribute for this channel, which is the raw attribute, which allows you to read the raw value from the converter. And there are also some shared attributes in this case, which would be the scale, which describes what the resolution of the ADC is, how you can get from the raw sample to a value in standard unit like voltage. And then there's some additional attributes like the channel number. Like if you have multiple channels, this would increase, 1, 2, 3. And here down here is a different example, temperature channel. And there's also something called a scan index. And the scan index is important for buffered applications. It says in which order, in which relative order, samples end up in the same sample set. So when you're reading from the buffer device, it will all be interleaved, all the data will be interleaved, and this scan index tells you in which order they will be. And it's not the absolute order. So if you, for example, have a channel with index 0 and one with index 1, and you enable both, that means 0 will be before 1. But if you only enable the one with index 0, this means index 0 will be the first one, and the same for index 1. And in addition, we have to this, each device driver has this I/O info struct, which registers read and write callbacks, which are used to access the attributes, the standard attributes. And then typically you have the I/O def structure, which is the representation of the actual device. You allocate it, initialize it, set up a name, point it to the channel you defined earlier, initialize the info attribute, and you say which kind of modes this supports. Some devices support only, no buffered mode. In this case, our example supports buffered mode. And then you register it, and that's it. So that's basically how simple kernel driver looks like. And let's move on to the user space ABI. And everything you've seen before, like all these kernel structures, are exported to user space through sysfs. Sysfs is a virtual file system that, well, instead of accessing a real file, you get these, when you read and write to these files, the callbacks earlier registered are called. And this is how all the exchange between the device driver and the user space application happens. And again, buffers are represented as character devices. So it's like with an input device or audio device, you can use read-write to the read-write calls to access the data in the buffers. And when you look at it, it kind of looks like this. So all I/O devices are in sys-bus I/O devices. You can take a look, and all the names follow this schema. So we see in this case there's 3 devices. And if we take a look at the first device, you can see the channels we registered earlier We have the voltage channel, which have all the raw attribute and this shared scale attribute. And then there's the temperature sensor, which has the raw attribute, the mean raw, and the scale attribute. And none of these are shared. And there are two subdirectories. One is for the buffer, and one is scan elements. But both of those are related to buffered input. We will get to those shortly. And the other ones here are just the standard sysfs attribute that you will find in every sysfs directory. And you can read the data by just catting the file. And you can also read other attributes like the scale. And if we multiply the scale by the raw value, we'll get the result in a standard unit. In this case, it would be millidegrees Celsius. So this is roughly 25 degrees Celsius. Moving on to the buffers. So the first directory is scan elements. And this is basically where you find 3 files for each channel. First, the enable one, which decides whether a channel is enabled or not. If it's not enabled, when you start buffered mode, there won't be any data in the buffer for this channel. There's, again, the index, which is the scan index, which was defined in the kernel data structure. And there's the type, and this type defines how the data is stored in the buffer. So first, we got the endianness, whether it's big endian or little endian, then whether it's unsigned or signed, then the number of significant bits, number of bits that contain real data, and then the second field is what's the size of the data word that it's stored in. So in this case, it's the 12-bit sample. It's stored in a 16-bit word. And the last field is by how many bits this is shifted. So for example, if your 12 bits in your 16-bit data word would be MSB aligned, this would be shifted by 4. And in this case, it's LSB aligned. And then for the buffer itself, there are only 2 attributes, enable and length configures the size of the buffer, and enables buffered operation or disables it. So if we want to capture data, we can do it like this, go to the device, enable the channel as we want, set up the buffer size, enable the buffer, read from the character device, which we can find in def, IO device 0, do something with it. Once we're done, this should be enabled. So once we're done, we disable the buffer again. And this looks all nice and great, right? You can use your existing tools like Echo and Cat, and all is great. So when you try to write a real application, this kind of gets really messy because you have to do a lot of string parsing, and as we've seen earlier, so in the kernel, this used to be a data structure that has a field in, has a field the index, and it also has a field which contains the attributes. Now it's all kind of flattened out in this one string, which is still where the different fields are separated by this underscore, and you have to take it all apart. And in some cases, one funny thing is the underscore is actually a valid character in the fields themselves. So taking this all apart is a bit complicated and requires some fuzzy logic if you want to do it right. It's not ideal. So and I think if you look at this, the target demographic of this was kernel driver authors, because it's really great if you want to test your driver. You can use Echo and Cat, it's great. But usually writing the driver is not the end goal that you want to achieve when you develop a driver. You actually want people to use your driver to do some kind of useful task. And if your applications have to directly talk to this interface, it gets really messy, and there's a lot of boilerplate code involved. And so that's why we thought about writing a library which takes care of all these tasks. And in this context, you should really stop thinking about, you should start to think about this as a serialized data stream. So the data structures that are contained in the kernel are serialized. all to strings, then export it to the sysfs, to the application. But the application itself shouldn't work on the serialized data. It should work on the unserialized data. And this is what the libiio is going to take care of. So let's talk about the libiio design goals. We want to hide all these low-level details of how to read and write the attributes, the files, how to find out which attributes exists, and take care of all the boilerplate code that's required by any application that wants to talk to a libiio device. And the other thing is we want to provide proper data structures like we had on the kernel, struct IO device, struct IO channel, and so on, instead of working with strings. So the libiio also takes care of reconstructing those data structures that were in the kernel. And then one more task we wanted to do is have a set of helper functions that are sometimes or often requires in applications. Not always, not each application might need them, but for a lot of tasks, there are a lot of repetitive tasks, and having these inside the libiio is really helpful, having them in a central place so that not each application has to come up with their own implementation. And one more design goal that we set ourselves early on is support for backends or remote backends. So this means we allow an application access to a device which is not running on. Let's assume you have kind of like an embedded board like a Raspberry Pi. You usually don't do the development on the machine itself. And it's quite useful to be able to develop on your development machine on your laptop, then just run the application on your laptop natively, but let it still talk to the real hardware that's connected to the embedded device that's running somewhere else. So the idea was to have a system daemon running on the embedded device, which then forwards all API calls to the real hardware, for example, over the network. Yeah. So let's talk quickly about libiio itself. So we started development at the beginning of 2014. We had the first stable release in August of 2014, and since then we've been trying to kind of like make 2 releases per year. I think this is a good number. We don't like say we want feature X, and we don't want to wait until feature X is implemented and is the next release, but like every 6 months, new release. What's ready goes into release, what's not ready goes not into release. This way we don't end up with a huge pile of features that never get released. Maintainer and lead developer is Paul. He has easily done 90% of the work that went into libiio, so he's the main contact point. If you have questions about libiio, new features proposed, talk to him. And it's written in a C programming language. I think it's still a good idea for a system library to implement it in C, because you can easily create bindings for a lot of different languages from C. But for example, if you would write this in Python, it's not so easy to like get your bindings to C or whatever. And we also have a stable ABI guarantee. So this means if the API or ABI was part of a release, we're not going to change it anymore. So if you're using libiio in your applications, you can be sure that it will continue to work even if a new release of the libiio comes out. And libiio is under, active development. I think we would hit like 1,000 commits at the end of the year. Not that it's any kind of interesting metric, but shows that it's still under active development. And of course, patches are welcome. If you have an issue, if you have a bug, if you want a new feature, send us a patch, we will merge it. So is there anybody in here who's actually already using libiio? 1 person, 2 persons. Do you have how's your experience so far?
Well, actually, we're using it for our project, the Acme Army group. But actually, it's not me who wrote the driver for that, so it's
Okay.
another guy from our company that we're using it. But I think
Yeah, I think I know. I think I know. Yes, thank you. I know whom you're talking about.
Yeah, marketing. It's better than Patamon for what you do for the high frequency.
Yeah, I'd say, I'd say it seems very tuned for reading high-speed voltages. You're also saying you support temperature, humidity, etc.
Yes.
It didn't seem to be very relevant to that.
Well, the company I'm working for is mainly making high-speed converters, so maybe that's why it's a bit biased in this direction. But in general, you can use it for all kinds of sensor devices because the interface is really the same in the end. Okay, so let's get to using libiio. This is a bit dry maybe and a bit of an API reference, and it's definitely not complete, but I want to give you a bit of a feel how this works, how the libiio works. You've already seen how the sysfs interface works, and now take a look at how the library interface works. And in libiio, everything starts with a context. The libiio itself has zero global state, which is quite important if you, for example, want to use a library from a different library, and then that library and the other library get used in the application, so they don't overwrite each other's state. So there's no global state, and all global state is contained in the context, which first has to be created, and you can create as many contexts as you want. And the context can either be local or can be remote. There's a function for creating a local context. There's a function for creating a network context where you specify the machine name or the IP address of the device where the IOD was running on. And then there's also a function called IO create default context. And this is the preferred function for creating a context because it allows the user to kind of overwrite which context should be used. There's an environment variable called IOD remote where you can set up either the IP address of the machine you want to talk to, or you can leave it blank, in which case it will use a local context. And sure. Hey. Can you use the microphone? Thanks.
I was wondering if when you open the local context, does it automatically export the connection for the remote context?
No, so when you create a local context, it will not open up a connection to the remote context. Was that the question?
Yeah.
No. So the local context will really only talk to this interface we've seen before, the sysfs interface, right? And the remote context will talk to a daemon running on a different machine, or maybe even on the same machine. And once you're done using the IO context, you have to call IO context destroy to free the context state, make sure there are no memory leaks, and so on. And we also have the devices, which are represented by struct IO device. This maps directly to the IO device registered by the kernel. To enumerate all the devices available in the system, there are two functions. One to get the amount of devices available, and the other one then to get the device by index. And there's also a helper function to find a device by name. You often know which device you want to talk to, so you can specify the name of the device you want to talk to, and then it returns the handle to the device. There are the channels. Again, struct IO channel, which maps to the channels of the device. And very similar to how you would enumerate the devices of a context, you can enumerate the channels of a device. It's very the same API. And again, there's a function for finding a channel by name. In this case, it takes an additional parameter, whether it's an output or an input channel, because there's an overlap in names for input and output channel. You can have an output voltage 0 channel and an input voltage 0 channel. So this one tells you whether you want the input or the output channel. Attributes. For the attributes, we didn't create our own struct. We are just using const char to reference to the attribute, because the attribute is really just the name of the attribute and nothing more. And as you can see here, again, very similar than before, you can enumerate all the attributes of a device, or you can enumerate all the attributes of a channel. And you can also look or search for an attribute of a device or a channel. And this is quite useful for checking if a channel an attribute actually exists. If it doesn't exist, this will return null. If it exists, it will return the same string as you passed in. But this string will be statically allocated and will be valid as long as the I/O context is valid. So for example, if you construct the name that you passed the lookup function on the stack, but you still want to keep the name around, you can use the value returned by the function to reference to the attribute later on without having to make your own copy. And so you can read and write attributes. Again, there's one variant for devices, one for channels. You pass in the device, you pass in the name of the attribute, and then your buffer, which contains the value that you want to write and the length of the buffer. Oh, sorry, this is reading. The buffer where you want to read the value of the attribute, and then the size of the buffer so we don't override it. And usually you are working with data structures that are not a string. Usually your data is an int or double, or maybe a Boolean, so there are a couple of helper functions to take care of this so you don't have to do your own string formatting. And so these functions internally convert the value that you passed in, or well, in this case, when you're reading, the value is read as a string from the sysfs, and then these functions convert them to the target data type that you want the value to be in. Very similar write functions, basically the same signature. You pass the buffer that you want to write, and then there are also helper functions for writing different data types like bool, double, and integer types. And now we get to buffers. So the first thing when you do buffered operation is you want to enable all the channels that you want to be included in this buffered operation, and disable all the channels that you don't want to be included. And then we have the struct IO buffer, which represents the active buffer. There's a function called IO device create buffer, which creates a buffer for a device. Specify the size, and there's also an additional parameter which is called cyclic, which is relevant for output buffers, in which case you can actually say, I want to repeat this buffer over and over again rather than writing new data, which is useful if you, for example, want to send out a test tone or something similar. You can basically put your application to sleep because the hardware will automatically take care of repeating the samples. And this is what this cyclic attribute specifies. And it's important to be aware of that this function does both configure and enable the buffer. So as soon as this function returns without an error, the buffer is enabled and data is captured. And once you're done capturing data, you call this IO buffer destroy function, which disables the buffer again and also frees the associated data structure. I will get to this. It's a very good question. I will get to this now. So there's a function called IO buffer refill, and this function does what you say. So this copies the data from kernel to your user space buffer, since you, from your application, can't directly access the kernel space buffer. So this will copy the data over. And then there is the function IO buffer start, which gives you the start of the user space buffer address. And what's very important to remember is that this might change after a call to IO buffer refill, because there are some optimizations where we might not copy the data, but we directly mmap it to user space. So we don't have to copy it, and if we mmap it, we might get different addresses for each refill operation. So IO buffer start might return the same address, but it might also return a different address. And to be on the safe side, always, after calling refill, call the IO buffer start function. There's another function called IO buffer step, which will tell you the spacing between samples in a sample set. So a sample set is when you enable multiple channels, the sample set contains the data for each channel that got sampled at the same time. And it's wrong to assume that if you, for example, only enable one 16-bit channel, that your step size will be 16-bit, because some devices have a restriction where they can't individually enable one channel. So in this case, the buffer might actually contain data from multiple channels, even though the user space application only requested one channel. So it's important always to use a step function and not assume that the size is fixed. And there's also another helper function which gives you the first or the offset to a specific channel in the data buffer. This is important for another reason. The data might not necessarily be aligned. So IIO requires that the data is aligned at the native size of the data struct. So if you, for example, have a 16-bit channel followed by a 32-bit channel, the 32-bit data won't follow directly the 16-bit data, but there will be a padding of 16-bit. And this all depends on which channels are enabled. So instead of having your application manually compute this offset, there's this function which gives you the first sample for a specific channel. And then you can, if you want to get the second sample for this channel, you just increase the address by the step size. So let's put this all together in a quick example. We have our three structures: the context, the device, the channel. We create the default context. So all this code is, of course, missing error checking. So usually you would check whether this succeeds or not, print an error if it doesn't. Then we look up the first device, look up the first channel of the first device. Then we set the sampling frequency attribute of the device to 1 kilohertz. And we also set the scale attribute of the channel to 0.525. So the scale attribute is which configures what the range of the ADC is. And some ADCs can be, for some ADCs you can configure the range. For example, there's an internal prescaler of the reference voltage. And for buffered operation, you have your data itself and the IIO buffer struct. First enable the channel, then create the buffer. This is the size of the buffer. We don't want cyclic operation. Call refill once, and then reiterate over all the samples. So if we call refill here, we will get the 1,000 samples requested here. And then we iterate over all the data in the buffer. And as you can see, we use the first function to get the first sample for our channel. And then we increment it by the step size, and we stop once we've reached the end of the buffer. And in this example, we just print the data. And once we're done, we destroy the context and disable the channel. And as you can see, or hopefully you can see, this is a lot easier than directly writing to the sysfs attributes. Probably take 10 slides or even more if we had open-coded all of this. The libiio also has a lot of bindings available for multiple programming languages. There are bindings for Python, there are bindings of C#, there are bindings into the MATLAB environment, and there are also experimental bindings for C++. Those are not part of an official release yet, but they are on a special branch. And since you usually can directly call C functions from a C++ environment, it's not high priority for us. And libiio is also cross-platform. This means if you write an application using libiio, you can actually, using a remote backend, you can run it on Windows, you can run it on macOS, you can run it on the BSDs. So you're not limited to Linux for running your actual application. And here on the right side, we see a quick example in Python. Import the libiio module, create the context, and then just print all the devices that are available in the system. So quickly talk about the IOD. So the IOD is a system service, and as I said before, the idea is that we have support for remote clients over TCP/IP, and we have some new development which enables us to use it over USB. And another thing the IOD does is multiplexing between multiple readers and writers. So the IO framework has a limitation that you can only have one reader and one writer at a time to one device. There might be multiple applications that want to access the same sensor at the same time. So the IO daemon takes care of multiplexing between those applications. And since the support for this is built into the libiio, it's all completely transparent. From the application's point of view, you can use the exactly same code to talking to the local backend and the remote backend. And another important feature is that the IOD allows us to track state. SysFS is by definition stateless. So if, for example, an application enables buffered operation or makes changes some settings and then crashes, all the changes made by the application will persist. And with the IOD, we can get a notification if the file handle over which the socket over which the application is talking to the IOD is closed, and then we know we can undo all the state or all the operations that were done by the application to get back to a state of minimum, for example, minimum power users. You want to disable all your buffered operations, so to make sure that things are not running when you don't need them to be running. And when you look at it from a schematic point of view, it looks like this. So we have the Linux kernel with the IO drivers. Here's the hardware. And the local backend talks to the kernel device drivers. And the IOD server uses the libiio to talk to the through the local backend to the devices. And then on a separate machine, there's also libiio using the network backend, and the application talks through the high-level API, through the network backend, through the IOD, back here, all to the devices. And we found this is actually something that a lot of people found useful to be able to run applications on a remote machine. Really quickly talk about the tools that we developed around libiio. So there's this tool called IO-info, which just prints information about your system, lists all the devices, lists all the channels, all the attributes, and the values, which is useful for getting an overview of what's present in your system. Have all your drivers been registered correctly? These kind of things. There's our readdef, which is useful for reading data. You specify the device from which you want to read, you specify the number of channels you want to read, specify your buffer size, and then just write it to a file or do some processing on the data. It's also useful for testing to see if, your data capture device is actually outputting any data. There's another one called IO Monitor, which is an N-curses-based application, which is kind of works like a digital multimeter. So you have a list of all the devices on the left side. You can select your device, and it takes snapshot values of all the channels available. So you can see here the temperature, the voltage channels, and so on. It's also useful for debugging, see if everything is working fine. You get the data you expect. And then there's the IO Scope, which is a GUI application which allows you to take a look at the data returned by the device. It allows you to look at it in time domain, frequency domain. You can also do constellation plots. There are markers available, so you can get information about where your tones are. And this is also quite useful for debugging, see if everything's working fine. Do you get the noise performance you expect from your device? And the IOD has also a couple of additional features where you can configure the devices, write the attributes from the GUI, and there's a plugin system which allows you to create a customized GUI for special devices. Like if you have a compound device, you have a couple of chips on a device, and on a PCB, and all these chips are working together, you can create a specialized GUI, like you can, not really see here. So this is a time domain view. You can see this also runs on on Windows, runs on Windows as well. And this would be a specialized GUI where you can configure all kinds of attributes of the device in a nice way. They are grouped by function and so on. So quickly talk about the future. I already mentioned we are working on a USB remote backend, which is implemented using the GadgetFS, FunctionFS interface. So you can take your embedded board like a Raspberry Pi and run the IOD on it using a USB interface, plug it into your laptop using a USB cable, and run all the applications on your laptop using your, talking over the USB cable to the I/O devices, which is quite useful in case you either don't have an IP connection or you don't want to set up the IP connection. Because if you don't have a DHCP server in the system, you have to either manually configure the IPs, and it's, well, sometimes a bit of a hassle. And the other feature that comes with this is support for backend operation, backend enumeration. So when you plug in a USB device with the USB IOD running, this API allows your applications to enumerate which backends are available, and then from there you can go and see which devices are available on the backend and so on. And the other things we are going to do is we're going to introduce a URI scheme to instantiate devices. So you would say USB : // and then the USB address. This is for local, and for IP you would use IP : / and the IP address. And this allows us to move away from the concept where you have to have one specialized function for creating a backend. So if we add new backends, we don't have to add a new function, and applications don't have to be updated. Users can just specify the UI they want to use, and then will automatically connect to the I/O backend at this URI. And for the long-term future, one thing that's missing currently from libiio is hot plug support. And this wasn't so much of a problem so far because most of the embedded devices have a static setup. If you change something, you recompile the kernel maybe, or you change your device tree, reboot. But for example, with device tree overlays, is changing, the system can be reconfigured at runtime. And we need to add support to this for the libiio. Because what you currently need to do, you need to destroy your context, then recreate it whenever the system changes. And that's not really user-friendly. And then another thing that's quite long-term future is make the remote backend support independent of libiio. Because one thing we've seen is this remote backend feature is so popular that people are starting to write drivers for the I/O framework instead of a different framework, even though the device driver would actually fit better in a different framework, like, for example, the HW monitoring system, like he said earlier. And the IOD is very much bound to I/O. But if we make this feature independent, we can actually add different data backends to it. We could sometimes, when you write an application, so because the way it is right now, it forces us to put application-specific logic into the kernel device drivers if we want to allow the remote application to directly talk to the embedded board. And this way you can move the application-specific logic actually in the daemon and don't need to have it in kernel space. And well, it also allows us to add different data sources. For example, think about GPIOs that you want to toggle in an embedded application, or there might be an EEPROM which contains calibration data that you want to read. And this is currently all not possible using the IOD. But conceptually, it would be really helpful to have this feature available. So this is really long term. And that's it so far. Are there any questions? Could you use the microphone? That would be really great. Thank you.
Sure. So I've got going back to the previous slide, you were talking about hot plug.
Yeah.
So you're mentioning device trees specifically. Would not hot plug be covered in the Linux device model if
Yes.
new sensors show up?
Yeah, so IIO, the framework itself supports hot plug. You can register a device at any point in time. But libiio won't recognize the registration of a new device unless you destroy your context and recreate the context, which means you basically have to stop your application, reinitialize everything, and that's not great.
So we need a method in the kernel of triggering that. That should be independent of description, though.
Yeah, no, it's well, the events are delivered as U events already.
Yeah.
It's already there. It's just that libiio doesn't support it.
Gotcha.
It doesn't handle it.
Gotcha. Yep.
over there.
So sorry, I missed a few slides at the beginning. Did you cover the difference between this and the LM sensor?
Between what?
Between the libiio IO and LM sensors. The
HWMon?
Kind of, yeah, HWMon. If you cover it, that's fine. I can show you a slide.
No, I didn't cover it, but it isn't also the scope of this talk, really. But one of the main differences is that HWMon doesn't support buffered capture. So IO allows buffered capture. Maybe looking back into the distant past, into the long time past ago, like 2009, when the IO framework was created, might have been a better decision to actually extend the HWMon framework rather than creating something new. But now we have it, and it's there to stay.
The question is, do you support data source from user-land application instead of from the driver?
Well, in theory, you could do it, but I wouldn't really recommend it, just simply because I don't like the idea. As I said, this would be part of this one. Part of this one, make the remote backend support completely independent from IO. So move this into the different library, and then you can add user space sources. You can add different kernel space sources and so on. But at this point, it's really specific to IO, to the kernel space IO framework.
The last question. I understand you want to implement the USB gadget file system. Did you consider to use USB gadget ether interface and USB
yes.
interface?
Yes. So as I said, we considered this. This was one option. But the problem is you need to configure it. It's not really plug and play. You either need a DHCP server or some other way to avoid conflicts in your IP addresses. You want to be able to plug in multiple embedded boards into your laptop without any conflicts. So static IP address doesn't work either. And with USB, there's automatic enumeration built in, and you don't get any conflicts.
But if you have used the USB gadget ether interface, you'll get a pair of USB interface. And it's like point to point.
Yeah, but you still need to assign an IP address to the interface.
That's true, but you can also use link, V6 link local.
Yeah, but you still need to make sure that there are no conflicts. So it's not that end user friendly.
Okay.
Over there.
Which protocol have you selected between IOD and the client? And do you know if there are Wireshark detectors for it?
So the question is which protocol we've selected for IOD and the application, between IOD and the application, whether there are any Wireshark selectors for it. So it's a custom protocol. At the moment, it's text-based. So if you look at it in Wireshark, you can actually understand it without any dissectors. Dbus. So the question is, why not Dbus? I'm not sure how to answer this. Maybe looking back, it would have been better to take a look what's available and maybe choose one of the existing protocols. But I think we didn't think about it, just implemented our own protocol. But there are definitely some deficiencies, and this also falls into this rework. There's some deficiencies in the protocol, so if we're going to rework the protocol to fix those deficiencies, we'll definitely look around what else is available, for, especially in the IoT sector, what we could reuse instead of coming up with a new own protocol. Yes, please.
On some of the new instances you were talking about lifestyle, etc. Who defines the attribute names for that? Is that the first person that comes up with the driver?
Yeah, kind of. Yeah, it's kind of by committee. You send a patch to the mailing list. The patch undergoes normal review. The maintainer will comment. Other people might also comment. And if there is agreement, then the new attribute names will be decided, or channel names.
Are those documented anywhere else apart from in the driver source?
Yes, so there's a directory inside the Linux kernel tree in the documentation which describes all the ABI of the I/O framework.
Right, because last time I looked at that, it seemed to have some specific parts were listed in there rather than an abstract definition, like if you want to be a temperature sensor, do this.
Now, so there are some part-specific files in case parts have custom attributes and custom channel types, but there's also a generic document describing all the generic attributes and channel types. Okay. Any more questions?
So each buffer will have, you'll have set up which channels you want sampled, and you'll have a certain order for those channels to be sampled within that buffer. How do you know then between buffers what the deltas are between the time that the first buffer was captured and the second? So that's the first question.
Yes, so, well, in the buffer we have the sample sets, and each sample set contains all the channels you have enabled, and the spacing between those sample sets will be defined by the device, and usually there's an attribute called sampling frequency, and this sampling frequency attribute describes what the spacing is between the samples. And if you do multiple refill operations, the idea is that you ideally wouldn't lose any data in between because there's double buffering in the kernel. So as long as your application can consume data fast enough, it will be continuous. And in addition to that, you can enable timestamping. So, and if you enable timestamping, each sample set will have a timestamp field, which will contain the timestamp of the time the sample set was captured.
The sample set being the buffer that contains multiple channel samples, or the channel sample itself?
The channel samples.
Okay, perfect.
Any more questions? Okay. The question is, how does I/O relate to comedy? It doesn't really. So comedy was, for a long time, basically dead. But it has recently been, well, kind of revived by some hard work by some folks. And yes, there's definitely some overlap, and we need to look into how to resolve this overlap.
Will it be possible to support one buffer where the sensor events are interleaved together?
Sorry?
So when you have different sensors, but they are interleaved in the same buffer?
No, this is not really supported. You would, well, in order to support this, you would have to have some kind of hardware aggregator to make sure that it's actually really the samples correspond to each other. And if they don't correspond to each other, the data is useless, so you don't need to have them in the same buffer. So if there's hardware, you would have to write a driver for it. If this hardware can aggregate the data stream together and make sure that the samples really match up, you would have to write a driver, and then you can have them in one buffer. So there's actually an API, in-kernel API, which allows you to access I/O devices from within another driver. And this way you can actually chain up drivers. Like if you have data capture devices and then the data aggregation device would reference the data capture devices. I think that's been around for like 1 or 2 years now. There's one more question.
So on the IIoT, when you have multiple clients connected to it, do you always pass the same data rate to all the clients connected to them, or do you allow multiple different rates?
Yes, yeah, that's an excellent question. So at the moment, if you have multiple clients connected, they have to be the same sample rate. There's no software resampling going on, mainly because this would probably overload the CPU in most embedded devices, and you would require some kind of hardware offloading support to do the resampling.
there are high-speed ADC type devices that can work in a half duplex mode that can be bidirectional. So how does your API support that?
If you are half duplex, you would you mean switch me transmit and receive?
Yeah.
Then you would have two devices, one for transmit, one for receive, and then independently access them.
And how would you describe, how do you time slice the operations? So
it's not really part of the scope of the core IO framework to do this. So you would have to register, a device which allows to configure this with custom attributes at the moment. So it's not part of the core at the moment.
Thanks.
Any more questions? Otherwise, thank you. And you can find further information at these addresses. So there's the source code in a Git repository hosted on GitHub. There's the API reference, which goes in a lot more detail than what we could cover here today, which describes the external API. And then there's the design document, which describes the internal API. So if you want to work on I/O, this is a really good starting point to familiarize yourself with the internal data structures and functions and so on. And it also explains some of the concepts that are used inside of libiio. Okay, thanks.